Okay, so I'll start. So this is going to be a course on cosmology, but I should say at the beginning that I'll assume that you know part of the cosmology that is covered in the general relativity course. I'll try to take about 2 lectures summarizing whatever we had learned in the last general relativity course. But in case you are not familiar, you should go back and study that part. Okay, because this will go reasonably fast. I'll not try to go through any of the derivations, and then I'll go into the early universe cosmology. Okay. And for those who are taking it for credit, marks will be divided into half of it will be an assignment, and there is in fact only one assignment, which I've already put up on the in the Moodle page, and you are supposed to submit at the end of the course semester. And the other half will be based on some project that you have to, it will be some reading project. You have to read up some particular topics and then give a presentation and write a project report. Yeah, it will be like a term paper and presentation, exactly.
Request from the timings of Wednesdays.
Yeah.
There's a class on Wednesday from 10:30 to 12. So can we start?
Yeah, the one is other people have class on Thursday and Tuesday. So what I have done is I have requested the academic office to fix definite slots for all the courses. Right? I think once that is fixed, I'll basically slide mine to the nearest slot. Right? But I think let them first fix it and then we'll try to do this. Any other question about the course? There is no tutor because there will be no homework assignment, right? Only one assignment at the end of the semester. So that I think I'll only grade. Unless there are too many people, and then in which case I may ask for a tutor. Okay, so let me then begin with the course. So first, let me just say that throughout these lectures, I'll set h bar equal to 1, c equal to 1, and the Boltzmann constant equal to 1. Okay, so this is the units that we'll be using. So, but by dimensional analysis, you can always supply back the powers of h bar c and the Boltzmann constant. Okay. Sometimes we also use G Newton equal to 1. But for now, I'm not going to use this. Okay, I'll keep explicit factors of G Newton whenever they are present. So cosmology is the study of the universe as a whole. But this is, of course, a very complicated object. Okay, so we study the whole universe, but on average. Okay, so we will not be able to predict what happens in different places of the universe, but we will study the universe, the average properties of the universe. And the first statement, okay, which is of course an experimental statement, that on the average, the universe is homogeneous and isotropic. Which roughly means that if you go to different regions of the universe, they look the same. And if you, so that's the meaning of homogeneity. And isotropy means that if you are at a given position of the universe, and if you look in all different directions, the different directions look the same. Okay, so this is the meaning of homogeneity and isotropy. And isotropy may sound similar to homogeneity. Okay, because if the universe is the same everywhere, then how can it look different in different directions? Okay. And a simple example that tells you the reference is if you imagine that you have a uniform electric field in space, right, in some z direction. Okay. Then different points in space, okay, feel the same thing, right? Everywhere there is a electric field in the z direction, so it's homogeneous, but it's not isotropic, because if you sit at one point, then the z direction is spatial, okay, compared to x and y direction. Okay, so isotropy, homogeneity doesn't mean isotropy. These are two separate properties, and both seem to be true on average. Okay, when you average over large distances. Okay. So this is summarized in what is called the FLRW metric, Friedman, Lachmer, Robinson, Walker metric. And that says that the universe, by choosing appropriate coordinate system, the metric that describes the whole universe on the average can be written as minus dt squared
Sir,
yes.
the camera is not moving. You went to the other side of the board, but it has not moved.
Actually, now I don't know who can fix it. Okay, can you just
Also, one thing, sir, could you explain how do we? Can you hear me?
yes, I can hear you.
How do you know that what is experimentally how the universe is isotropic and homogeneous? Like what measurements has been done?
Yeah, so this one I had discussed in the last semester in the GR course. Okay, so basically it's indirect conclusion, right? You work out the prediction of homogeneity and isotropy, and then you can verify it, right? Of course, you cannot go to different regions of the universe and measure the properties, right? But assuming that the universe is homogeneous leads to various indirect predictions, and those you can verify in experiments. Right, so it's part of the experimental observation. So, as far as experiment is concerned, we can only sit in one place and look in different directions.
Yeah. Okay, thank you.
I think you discussed this in last year course. So this is the most general homogeneous and
Isotropic metric, yes.
Most general.
Yes. Right. So in homogeneity and isotropy is in the spatial direction. Right. So T is a spatial time coordinate. Okay, this is it's not a coordinate independent statement that the metric takes this form. So the statement of homogeneity and isotropy is that there is a spatial time coordinate. So that if you choose that particular time coordinate and then you look at the constant T surface, right, where the metric is given here, then this metric is homogeneous and isotropic as far as spatial directions are concerned. Okay. I haven't said what K is. Okay, rho, theta, and phi are just coordinates. Okay, rho is the radial coordinate and theta and phi are angular coordinates. So K takes value 0, 1 or minus 1. 0 corresponds to flat universe. Okay, that's clear, right? If K is 0, then this is just the Cartesian metric, right, written in polar coordinates, d rho square plus rho square d theta square plus rho square sine square theta d phi square. K equal to 1 corresponds to sphere. Okay, you can show that the corresponding metric for K equal to 1 describes a three-dimensional sphere, right, which means a surface which is, you can think of the three-dimensional surface which can be embedded in 4 dimensions by writing an equation x square plus y square plus z square plus w square equal to 1. And K equal to minus 1 is what is called a hyperbolate space. Okay. Now it's useful to introduce a slightly different variables, and a of t is some function. Okay, a of t is some function of t. Is the camera problem solved or not yet?
Yes, sir, it's solved.
It's solved. Okay. 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 Now we'll use this notation that T0 is today's time. And we will define A0, which is A of T0. Is there some other mic here? No, there is no other mic, right? So maybe this one. Off. So then we will denote this quantity lambda t which is A of t over A0. And now we can write this A of t as A0 square times lambda of t square. Yes.
How do you define this t coordinate? When you say today's time, what does that mean?
Yeah. Okay. I'll describe this. How do you define the t coordinate? Yeah. So the origin of time is fixed by requiring lambda t equal to 0 to be 0. Okay, so that fixes, so at whatever time, whatever value of t, the lambda is 0, right? That will count as the origin, and then t0 is today's time. But this one I'll try to discuss in some detail later. Okay, so let's define a new coordinate R, which is rho over rho A0. Yes.
This A of t, are there any constraints on what kind of function they are?
Well, that it will have to satisfy Einstein's equation, and that will determine A of t. Right? Right now, you are not saying anything about what kind of function A of t is. Right? But we will see that A of t is a monotonically increasing function of time. Right? And at some point, it becomes 0. Right? And that's how you count the origin of time. Yeah, but right now, A of t is just some function. Right? You have not said anything about what A of t is.
The A of t to start from 0. It should attain some 0.
Yes. So, I mean, that's why, I mean, this is somewhat premature to say that this is the way it is defined, right? But we will see later, right, that there is a point where A of t is 0, and that's how you start counting time. Okay? Right now, you can say that, okay, t0 is today's time, whatever coordinate system you are using, right? You don't have to say this at this stage, Okay, T0 by definition is what is today, right? And A is what is the value of A today, A of T naught.
By definition, is lambda T at 0. So is this equal to 1?
Yes, lambda at T equal to 0 is 1 by definition, indeed. Sorry, T equal to T naught. Lambda at T equal to T naught is 1. We'll move it down. Okay, so I think this is a mistake here. So we take R equal to A naught times rho. And in this coordinate system, you can check that dA square becomes minus dt square plus lambda of T square. Okay, just change variable from rho equal to R over A naught, and you will find that that metric that I have written here becomes this. And now, based on today's observation, again, we'll later see what the observation is. Based on today's observation, we cannot distinguish K over A naught square from 0. Which means that whatever experiment we can do today, right, K of A naught square is consistent with 0. Right? You can never measure something with absolute accuracy, right? But whatever accuracy we can measure, we can say that K over A0 square equal to 0. Okay? And that means that based on today's observation, we cannot really distinguish between K equal to 0, 1 and minus 1, because A0 is so large, okay, that is as good as setting K equal to 0. Okay? So, in other words, that for any calculation that we want to do for today's, for the universe that we know, okay, we can simply set K equal to 0. Right? We will keep K for some time, because ultimately you want to know why K over A0 square is indistinguishable from 0, right? How it's measured. But once you accept that it is measured and it's indistinguishable from 0, we can just set K equal to 0 in all our calculations.
But so in early universe, it would have been that it would have played some role.
Yeah, we'll see that even in the early universe, it doesn't play any role. That also will argue, right? Why it doesn't play any role even in the early universe. Neither in the early universe nor in the late universe will it play any role. Right? But for that, we have to wait and look at the set of equations that tell us how A changes with time. Okay. So these coordinates, the r theta phi, or equivalently, we can change to Cartesian like coordinates, right? Because if this is 0, then you can always change from r theta phi to xyz Cartesian coordinates, right? Or xyz.
Within this statement, it becomes something that coordinate dependent statement. This coordinate.
Yes.
K by A0 square becomes very small. That's why it becomes an indistinguishable. Coordinates that we used previously.
That is true. But if in any coordinate system, you can make it nearly 0, that is good enough, right? Because sometimes by changing or choosing a complicated coordinate system, you can pretend as if you have many parameters in the metric, right? Ultimately, I mean, as long as you can simplify it by choosing some coordinate system, that is a good enough argument, right? So any coordinate system will be fine. What is a scalar? Now, no scalar, because this is not a general coordinate invariant. Okay, you can say Riemann tensor. The square of the Riemann tensor is 0, right? We will see. Okay, Riemann tensor is still not there, right? Because you have to talk about the spatial slice. Here you are talking about only the spatial slice, right? So in this slice, for example, right, the three-dimensional Riemann tensor square, the invariants are all very small. Right? That is a statement. And that you can see once you have written in this coordinate system.
Then that shouldn't depend on whether you write A of T or lambda.
Whether you write A of T or lambda of T.
If I just took this spatial slice.
Yeah. So if you multiply by A0, right? You have to multiply by A0. A0 is important, right? Because if you take a sphere, right, it's curved. But I take a sphere of very, very large radius. That is almost flat locally, right? So that is the overall coefficient is important. Right? And that's what is happening here, right? This may be a sphere, but if you take a sphere and you take a very large radius, right? Multiplying by a constant means that you're taking a very large radius sphere, right? That's almost flat. Right? And what it is saying is that the sphere or the hyperbola is such a large radius that whether it's sphere or hyperbola, you cannot see by current experiment.
About that statement about which scalar is becoming 0.
Yes.
I can say this about any parameter in metric that I can extract it in a coordinate independent way, right?
Yes. Not any parameter. Because if you take two different metrics which are related by coordinate transformation, you can introduce a lot of parameters into the coordinate transformation, right? But in the scalar, it will go away.
So K is like any parameter.
K is
I don't know.
K is okay. K is one of the parameters, right? Okay, maybe I can say K over A0 square is a parameter, right? K over A0 square is small. That's this parameter is a physical parameter of the metric, right? And K over A0 square being small or big makes a difference because it tells us whether the spatial slice is highly curved or very it has very small curvature, right? But there can be other parameters that you can introduce by coordinate change,
Okay.
right? Which are just coordinate transformation parameters.
But that coordinate transformation would be 1, 1.
One, yeah, you can have a one-to-one coordinate change.
And R theta phi I can take it to X, Y, Z.
Yes, and the Riemann tensor is 0 in all of them,
Right.
right?
But what parameter am I introducing here?
Oh, I could have made multiplied by some constant b. Yeah, the b will be a parameter, right?
Okay.
If you start from x, y, z, right, and introduce a parameter b somewhere here,
But
right?
that won't reflect in.
In the Riemann tensor square, it will not reflect, right? Because the scalars are all 0. Pardon?
Aren't you missing an R?
Yes, I am missing an R in all of this. So whether you use r theta phi or x, y, z, right? These are called co-moving coordinates. Right? These are spatial coordinates, right? Because you have chosen, I could have taken a general coordinate system in which time and space gets mixed up, right? Those will be complicated coordinate system, right? Which we can use, of course, if you want, but things are obscure in those coordinate systems, right? So the co-moving coordinate system is this one. So these are called co-moving coordinates. And one physical significance of these coordinates is that on the average, objects in the universe are at rest in these co-moving coordinates. Which means that if you take a particular star, it has some location, right? Some space-time coordinate is described as some space-time coordinate in the universe. And you can ask, as time changes, how do x, y, and z change for that star? Now, for a particular star, x, y, z is not time independent, but the time derivatives are small. Okay, small means what? Small compared to the speed of light, because I've said c equal to 1, right? So whenever I say that dx dt is small, that means it's small compared to speed of light. So co-moving coordinates are the coordinates in which, on the average, bodies are at rest. Okay, fixed r theta phi or fixed x y z. But there are small fluctuations in actual practice, right? Stars have relative motion, right? Not all stars are fixed with respect to each other. Those small relative motions are captured by saying that dx dt, dy dt, and dz dt are not exactly zero, but they are nearly zero for objects in the universe. Is this clear? Not clear? Yeah, I'm assuming it's clear unless you ask.
So one small thing. So
Yes.
I mean, they are you are saying, I mean, it is small with respect to what?
Speed of light.
Speed of-
Because I've said c equal to 1, right? So when I say dx dt small, right, that means the compared to speed of light is small. I mean, the stars, for example, move at speed of a few hundred kilometers per second, right? With respect to each other.
Timescales that are very large.
Yeah, so you can consider time scales that are very large. Over very long time scales, stars may move a long distance, right? But that's okay. That's not problematic, right? Okay. The point is dx dt is small. That's what is needed.
So I mean, since you're saying that this is a coordinate dependent statement, we're basically saying that in these coordinates, the dx dt, dy dt, or di
Yeah,
dt,
in these coordinates meaning the specific coordinate system in which time and space has been split.
yeah. So what I was trying to ask is, if I computed the proper velocity of the star, should that be small?
Yeah, that will also be small. Proper velocity, okay. Proper velocity of everything is 1, minus 1, right? So, meaning in the, so what do you want to calculate?
No, when you say proper velocity, the proper speed is minus 100. U alpha, for example, dx d tau, where tau is the proper time of the.
Dx d tau, but when you take the dx d tau dot dx d tau.
Yeah, let's say I'm not doing that. Components
Yeah, dx d tau, okay. Dx0 d tau, of course, is 1 in this case, right? Almost. Because if we have, okay, suppose we have a particle that is at rest in the co-moving coordinate, right? Then these are all fixed. R theta phi are fixed, right? So ds square is minus dt square, right? So that means for co-moving objects, t is a proper time, right? So this time coordinate t has a special role, right? This is a proper time for co-moving objects, right? So dx0 dt for a co-moving object is 1.
What does mean to say it's a co-moving object? I mean, I can move it as fast as speed as I want.
So you are not co-moving then,
so
right? Co-moving object means objects for which this is small or this is 0, right?
So
Strictly co-moving objects are the ones for which dx dt, dy dt, and dz dt are 0.
and the statement is that stars are co-moving.
Yes, the statement is stars are approximately co-moving, right? Not that they are exactly co-moving, they are approximately co-moving. Yes.
This is a question, but should we ascribe all this analysis to individual stars? I mean, as far as I understand, stars themselves are not expanding in this movement.
Yes, indeed.
There are galaxies which are expanding.
Well, stars are fixed in positions, right? You are talking about the relative distance between the stars. Yeah, that's because they have additional gravitational force, right? So that's why they are not expanding. That's what you mean, right? For objects which are out of each other's gravitational force, those will be expanding. So this is the average background wave, right? And this kind of formula that I'm going to give, right, are results of averaging, right? So you take, you're right, it's individual stars, right, are fixed in the galaxy. So you have to talk about the velocity speed of the galaxy, right, how fast it is moving. But there is a different way of saying it, that the co-moving frame, right? Okay, the microwave background that I have not introduced so far, but we'll do it soon. That the universe has a microwave background radiation, 2.73 Kelvin, right? And that microwave background radiation is isotropic in a very particular frame, right? Clearly, if it's isotropic in one frame, it will not be isotropic in a moving frame, right? So that is a co-moving frame. Right? That's another way of defining co-moving frame, where the cosmic microwave background radiation is isotropic. And in that frame, then you can say co-moving speed of its star is the speed at which it's moving relative to the cosmic microwave background radiation. That's one way of. So if you want to measure the co-moving speed, your co-moving speed, right? You look at the cosmic microwave background radiation, find an anisotrope, right? What is the difference between temperature in this direction and that direction? Okay? That will tell you how much speed you have with respect to the microwave background radiation, and that is your co-moving speed. Okay? That's a practical way of determining your co-moving speed.
Want to go to a frame in which the cosmic microwave background seems isotropic.
That's the co-moving frame.
Statement here, since we have not done any GR, so since we are writing down this metric, the statement here is that there is a frame in which, not coordinates, but there is a frame in which it looks isotropic. But
Yes.
If you go out there and do an experiment, you're saying that the frame in which it could look isotropic is the frame adapted to the scheme.
Yes, indeed. Right? Why that is the case? That of course we will learn much later. Right? But in practical terms, if you want to know what is the frame in which it is isotropic, it is CMB. Right? The CMB is isotropic in this frame.
But to me on the earth, the CMB will not look isotropic because
No, yeah, indeed. So if you look at the CMB spectrum, right, you do find an anisotropic, right, which is ascribed to the local speed of the Earth, for example.
The velocity of the star is pretty large, say some near.
Yes,
Then
that is not a co-moving object. Yeah, so indeed, if the speed reaches near the speed of light, then it's not a co-moving object. You cannot approximate it by a co-moving object.
when we talk about even a star, we're talking about an average speed in some constellation.
Exactly. Yeah, exactly. Right. So if you're asking if there are objects in the universe which are not co-moving, there certainly are.
but neither of us is also common.
Who? Neither of. Yeah, we are not, because we are on the Earth, right? We are moving through the microwave background. So if you measure the microwave background temperature in the different directions, you'll find a difference.
Doesn't matter because when we deal with FLRW metric,
Yes,
we are talking about scales of some 100 or 500 megawatts.
exactly.
So it
Yeah.
doesn't matter what happens.
No, it doesn't matter, right? But it matters when you're trying to make measurements, right? Suppose you want to make measurement and find out how does a microwave background look, right? Does it agree with what theory predicts, right? There it will matter because you have to correct for your local speed, right? And only then you can compare with theory.
Kind of corrections done from the experiment themselves. They will measure something and they will extract out what the, for example, they will compensate for the Earth's rotation or something.
Exactly. Yeah. Yeah. Yes.
You are saying that some frame cosmic microwave background is isotropic. So isn't it we have specified a frame that is different from others? So if we are
Yes, indeed. So that's why in cosmology, right, we have to work in a spatial frame. It only in a spatial frame that things are simple, right? So when you say the universe is homogeneous and isotropic, right, you can give it as frame independent meaning. What you mean by homogeneous and isotropic? But it can be made manifest by choosing a spatial frame, right? And in that frame, the metric looks like this, right? Or equivalently like this. So it requires choice of a spatial frame. Any other question?
Sir, actually,
Yes.
can you comment on what?
Oh, no, that I will do afterwards. That's not part of this course, but we can certainly discuss that, or you can even write a project, right? You can take your term paper on that, right? That's an alternative cosmology proposal, right? But we will not discuss it. I'm sorry. Right now we are just discussing standard proposal for cosmology. That is experimental, right? That we can, this notion of isotropy, right, and homogeneity, as I said, that's something that is a question. How do you know the universe is homogeneous and isotropic? Now, of course, you cannot know directly because you cannot go to different places and do experiments, right? You can sit in our position and do experiments in all directions. But from those measurements, you can indirectly figure out how the universe will look in a different region of space, right? And from that, you conclude that the universe is homogeneous and isotropic. There exists a frame, right? It's a highly non-trivial statement that there exists a frame in which the universe is homogeneous and isotropic. But experiment tells us that there indeed exists such a frame, right? Initially, when people started modeling the universe by this FLRW metric, right, they took it just as a simplifying approximation, right? That time there was no evidence that the universe actually looks like this, that it's homogeneous and isotropic. Now we know that the universe actually looks homogeneous and isotropic, right? But that's after a lot of experiments, right? And the explanation of this comes from inflation, which we'll discuss maybe near the end of the course, right? Why the universe is homogeneous and isotropic. Okay, so then as far as current observation is concerned, we can take this metric to be the spatial metric to be flat. And do our calculations, but as I said, I'll keep this K in some of the calculations where things are not difficult to do. Okay? But whenever you find that you are having difficulty doing some integrals, we'll just set K equal to 0. Okay, because for all experimental purposes, that's good enough. Okay, so now let me discuss some consequences. The first consequence is redshift. So consider a star, a co-moving star, at A, and a co-moving observer at B. And we can, because the universe is homogeneous, right? We can take A and B to be any position you like. Right? Let's start with B, and we'll take B to be at the origin of space, R equal to 0. Okay, let's take B. This is at R equal to 0, and there, of course, theta and phi doesn't matter. But let's say we put theta naught phi naught. That R equal to 0, really, the polar angles have no meaning, right? At the origin, right, all polar angles are the same. That's the same point. Now for A, I can take R equal to R naught, and because of isotropy, I can choose this to be any direction I like. Right? I took it to be theta naught phi naught. Because if you look from B, right, whether A is in this direction or that direction should make a difference. Right? Only the radial position should make a difference because of isotropy. So you can take A to be R naught theta naught phi naught. Is it clear? Right? So B at the origin, that's the source, that's the observer, say us, and some far away star at R naught theta naught phi naught. Now let's consider, let's suppose that light emitted by A at T1 reaches B at T1 prime, okay, and then light emitted by A at a later interval, say T1 plus delta T1, reaches B at T1 prime plus delta T1 prime. Okay, and delta T1 and delta T1 prime are small in cosmic scale, right? It just changes a little bit, a little later. So the light travels along null ray, ds square equal to 0. Right? So this means that dt squared should be a of t squared times dr square over 1 minus kr square plus theta and phi. I'm going to argue that these are 0. Now, imagine that we are looking at the light ray sitting at B, that's the origin, okay, and the light has come from A. The claim is that the light will travel from A to B at fixed theta and phi, theta naught, phi naught, right? Now, let's see why this is the case. Let's suppose that's not the case, right? The light bends, right? We don't know, this is the Card space-time, right? It could have happened, the light bends and reaches this. So it say, suppose it reaches B along some other curve, right? Not fixed theta, not phi naught. But then you see that from A, there is a line of sight, fixed theta naught, phi naught, that is B, right? And you are saying the light comes not from that line of sight, but some other direction. I shouldn't say line of sight, right? Because line of sight is where the light comes from. Okay, but whatever. Suppose the line of sight is not along theta equal to theta naught, phi equal to phi naught. Okay. Then by isotropy, right, you can rotate. Right? And if the line is, if the ray is not coming from the theta naught, phi naught direction, okay, but some other direction, then its rotated version is equally likely for the ray to come from. Is that clear? Right? Okay. If you think in terms of flat space, it will become clear, but it's also valid for non-zero K. Right? Imagine that you have flat X, Y, Z, right? And you have taken the other object, the source to be on the Z axis and the observer to be at the origin. Okay? And now you are asking that if the source emits a light, right, does it travel along Z axis and reaches the observer, or does it go along some other curve? Okay? If it did go along some other curve, right, then it will be conflicting isotropy, because if it goes along this curve, right, then by rotating the system, right, it doesn't change the position of the source or the position of the observer, right, because observer is on the both are on the Z axis. But by rotating, you will conclude that light doesn't come along this, but it comes along a rotated direction. Okay. So imagine that you are saying that it comes along it moves a little bit along the X direction. Then why not along the Y direction? Right? Because you can rotate about the Z axis. Okay. So just from this symmetry, you can argue that the path that light takes will be at constant theta and phi. Okay, theta naught and phi naught. Okay, we could have taken, for example, theta naught equal to 0, which will correspond to the Z axis. Okay. If the source is along the Z axis, then light better come along the Z axis. So this part will be 0. And now we can write dt as now notice that I have put a minus sign. And this minus sign reflects that as t increases, R decreases. It was just because of a geometry, right? Because we have taken the observer to be at R equal to 0, right? The source to be at R non-zero, right? So as the light travels from source to the observer, the value of R change decreases, right? But of course, time will increase, right? Everything moves forward in time. That's why I have chosen a minus sign here. Sorry, lambda of t. Thank you. Pardon? Oh, first one also. Thank you. Yeah, because I'm using this form of the metric. Now let's integrate this. So integrate from T1 to T1 prime dt over lambda of t, right? I just took the lambda of t on the other side is minus integral from r0 to 0 dr over square root of 1 minus k r square over a0 square. Right, because it starts at T1, it reaches at T1 prime, right? Look at the geometry. Starts at T1, reaches at T1 prime. Right? So the left hand side is integrated from T1 to T1 prime, right hand side, it starts at R0, reaches at 0. Now we have a similar equation, because if it starts at T1 plus delta T1, okay? Is it okay? R0 to 0, thank you. Minus. Now take the difference between these two. When you take the difference, this part gets cancelled. And what you get is delta T1 prime over lambda T1 prime is equal to delta T1 see the same integral, right? Only the limits have changed. Right? Here instead of T1 prime, we have T1 prime plus delta T1 prime. Right? So this gives you delta T1 prime divided by whatever the value of lambda is at that end. Right? And similarly here, it's delta T1 over lambda. So this tells us that delta T1 prime is delta T1 times lambda T1 prime over lambda T1. That the difference between two signals, right? That if you have two signals emitted at an interval of delta T1, right? And what you observe is not the same interval delta T1, but a different interval delta T1 prime. Okay, and that is given by this formula. Now suppose we are talking about this signal as some wave being propagated produced, right, with some period. Right? Imagine that you start at the star A, right, and it emits a wave with certain period. Right? It could be the period of the light signal itself. Right? Anything, any signal, any oscillation. Then the frequency of the wave, right, is inverse of the period, right? So nu prime will be nu times lambda T1 over lambda T1 prime. And this nu prime is something we are measuring. Right? We take a light signal and we see what, so we can measure what frequency is coming to us. Observation tells us that nu prime is less than nu. This is called redshift. Now you may wonder, how do you even know what nu is, right? We only see what we are observing, right? We don't know what its frequency was when it was emitted. So the reason that we know what nu is because we don't measure just one signal, right? We basically measure the spectral line, okay, the whole spectrum, okay, which basically you can identify with various molecular transitions, right? Stars have certain spectrum, for example, from various molecular transitions, right? Atomic transitions. So you compare the whole spectrum that you see from a distant star, okay, with what you see in your laboratory. The ratios are not going to change, right? Because you can see that it's the same, the factor by which it changes doesn't depend on what the original nu was, right? Nu prime over nu ratio is the same, right, irrespective of what the original nu was. So what you do is that you look at the signal that you are observing, the whole spectral line, and then you can identify which line corresponds to which particular transition, because you know the ratios. Ratios are unchanged from where it was emitted. So by comparing the ratios of the spectral lines that you observe, okay, to what you actually see in the lab, okay, we know how much each spectral line has gotten shifted. Yeah, that's how you measure this nu prime over nu ratio. Yes.
T1 prime is later than T1, right?
T1 prime is later than T1, indeed.
Lambda T prime should be greater than lambda T.
Yes. No, lambda T1 prime is greater than lambda T1, right? So this is less than 1. That's why nu prime is less than nu. Yes, that will be the conclusion that will be drawing from this. Right now, the observation is that nu prime is less than nu, and I'm just trying to explain that how is it that you know nu, right? Nu prime we measure, right? Nu we don't see directly, right? But you know nu indirectly because you look at the whole spectral line, okay, and then compare with the spectral line that you observe in the lab. So by looking at matching the ratios correctly, you know which line corresponds to which particular transition, molecular transition, right? That's how you know what nu is.
Just one question.
Yes.
Would the functional form of lambda T itself change with the later
Yes.
some lambda T?
True. But the point is, the time span over which you're making the observation, right, is so small that its lambda doesn't change in that time span. Okay, that's why I say delta t is small compared to in the time delta t. Right, as I'm saying, lambda t is not changing very much. Right? Lambda, in fact, changes very slowly. Right, it like lambda doubles in 10 billions of years. Okay, today. So clearly, that change is not going to affect things. So is this point clear? Right? Yes.
What exactly observing is only just the prime values.
Only the prime values, yes.
Not even the ratios.
No, not even the ratios, but we observe the prime values, right? We observe this. Okay, it's not uniform. We also observe various transitions. Something like this, right? Okay. Now you compare with the spectrum that you know from the lab, right? What kind of spectrum various transitions have. Okay. And you find that this compared the spectrum is something like this. You match the ratios of these with the ratios that you see in the lab. Right? By comparing that, you know which line will correspond to which line. Right? For example, the ratio of these two, ratio of this to this should be equal to ratio of this to this, ratio of this to this, and so on. Right? And this matching, if you make a misidentification, suppose you identify this line with that line, right? Then the next line is here much farther away, right? So you'll not be able to match the ratio, right? So by matching making sure that the ratios match between what you observed in the lab and what you observed from the stars, okay, we can figure out which line corresponds to which one. Right? And that's how you know what nu is. Right? You know, you observe nu prime, but once you observe nu prime for many different lines, you can figure out what the corresponding nus are. Right? And that's what you use to figure out this. Okay. And as Rishabh just said, that because nu prime is less than nu, right, this means that lambda T1 prime is larger than lambda T1, and hence the universe is expanding. Other questions?
This metric we have taken in cosmological scale. So time limit, say one star is too much far away from Earth, the time it will take to reach the ray.
Indeed.
Then
Yes, it will indeed. So for different stars, right, at different distances, the redshift is different. Right? The farther away the star is, the more redshifted it will be because it will take longer. That means the light that is coming, right, was emitted much earlier. Right? So this ratio lambda, so what I'm saying, the farther away the time star is, right? T1 prime is fixed. That's today's time. We are making the observation today, right? The farther away the star is, the smaller is should be T1. Right? Because it must have started very early. And hence this would be different. Right? And that's the way we actually find the T dependence of lambda. That's one way at least, right? Observing farther and farther stars. And from that you can figure out how lambda is changing with time.
from that we will get that this is not.
Exactly. Right? And we'll actually discuss this in a few minutes. Yes.
So when drawing the final conclusion that the light is redshifted,
Yes.
so at the back of our mind, we are presupposing the wave picture of light, right? For example, if I had a source which is emitting, individual photons one at a time,
Yes.
then my conclusion would just happen that there's no change in the.
Oh, energy also gets redshifted. We'll see it later. So there's no conflict with quantum mechanics. Otherwise, there'll be conflict with quantum mechanics, right? If the
Even if a single photon is emitted, the
energy will get redshifted. It will lose its energy on the way. Right? That's because of the expansion of the universe. So this is indeed the case. Right? I mean, you can take a photon of energy E, right, and study its motion in this background. Right? Just solve the geodesic equation. Right? And you will see that effective energy actually goes down.
Can I reach the same conclusion by just solving the wave equation for light in curved space?
Yes, you can. Right? Because after all, whichever you arrive at the conclusion, right? It should, if it's a physical result, it should always give the same answer. Okay, so now I'm going to give some definitions. So if we take lambda t over lambda t naught, lambda t naught is 1. T naught is today's time. Okay, so lambda t naught by definition is 1. We can try to expand it in a Taylor series expansion in t minus t naught. Okay. So the first term, of course, is 1. Right? At t equal to t naught is 1. Then we have some constant times t minus t naught. This is what is called the Hubble constant. This is today's expansion rate. The next term we parameterize by minus half q0 h0 squared Q minus T naught square plus higher order terms starts with
Oh, sorry.
yeah, lambda T naught I have divided by, right? Okay, lambda T naught is 1, right? So like say it's really expansion of lambda, right? I have explicitly written this lambda T naught just so that it's clear that it's 1, right? But this is just 1.
That sounds like lambda T starts from 1.
Yes. And at T equal to T naught, indeed lambda T is 1, right? By definition, because lambda T is the ratio of A of T divided by A at T naught. Okay, so here I have just chosen to parameterize in this particular, there is some constant, right? I have just extracted out a factor of H0 square and call that constant Q0. This is what is called the deceleration parameter. Okay, and this has been measured. And what one finds is that Q0 is actually negative. This from measurement. Okay, this basically means that the universe is accelerating. The expansion is accelerating. Is this okay? Right, these are just definitions.
So the one must draw from this Q0 becoming negative is like the universe, right part of our so the universe is expanding or the universe as a whole is expanding.
Universe as a whole is expanding, right? Because this is the expansion of the universe on the average, right? The metric is changing.
So it's like the expansion is over near some T0, assuming some time difference, right? So we are looking at some small times.
Yes, indeed. Yeah.
Some small part of the.
So currently, right, the universe is accelerating. Doesn't mean that the universe is always accelerating, right? Or the universe will always be accelerating. But this by itself doesn't say anything.
Okay.
Right? It only says that currently the universe is accelerating.
Okay. And expansion is happening at all times.
Expansion will happen at all time scales, right? That's because lambda T will keep increasing, right? Okay, that follows from the equation that will derive for lambda T. Right now we have not written down any equation for lambda T, right? And that those equations will make clear that lambda will keep increasing.
At the present approach, the universe is accelerating.
Yeah, in the present epoch, the universe is undergoing accelerated expansion. Okay? That's all this particular observation says.
Q0 is small.
Pardon?
There is dimensionless piece here, right? So Q0 is small.
Yeah, everything is small, right? The expansion rate of the universe is very small. Otherwise, see, our universe locally looks flat, right? Minkowski, right? And that, why is it Minkowski, right? It's Minkowski because lambda dot is really small. Okay, in conventional time scale, as I said, lambda doubles in about 10 million years. Right? That's roughly the kind of expansion that you are talking about. Right? Lambda becomes, which is a statement H naught is small, right? So all the parameters are actually small.
I was asking that because say if you kept the third term will be parametrically smaller than H0 and Q0.
Compared to H, well, no, once you have extracted H naught square, right? Yeah, then these are of order 1. These are dimensionless objects.
Okay, so then once you have extracted H0 cube, that coefficient also
Will be of order 1.
Oh, but the terms are getting parametrically suppressed by H0.
Exactly.
Is there time dependence in Q0? So you said that in the past.
No, Q naught by definition is constant. It's the second derivative today.
Yeah, so if it is negative today, it must have been negative at all times.
Yeah. Okay. The Q naught is negative. That's it, right? Q naught is a constant. It's negative. Right? What could have happened is that Q naught negative means lambda double dot is positive today, right? because this is t minus t naught square coefficient. Lambda double dot need not have been positive in the past. Right? And at this stage, you are not even saying the lambda double dot will remain positive in the future, although that happens to be true, but that requires theory. Right? From current observation, all we know is the lambda double dot is positive. Is it clear? Okay, then I'll introduce some more definitions. Now, there will be a lot of definitions. Redshift. So Z of t by definition is 1 over lambda of t minus 1. Okay, you can think of this as a measure of time, right? Because Z, suppose you have observed some redshift from a star, right? What does Z tell us? Z tells us that what was the time at which the signal was emitted that we are receiving today, right? Z contains that information, right? The further away the star is, earlier the signal would have started and Z would have been larger. Is that clear? Earlier means lambda would have been smaller. See, today lambda is 1, right? So Z is 0. That's how we have defined it. Okay. Far away stars, right, would have smaller t, and so Z would be positive, right? The farther away the star is, the smaller would be lambda of t, and then Z will be more positive. So Z, you can think of that as a measure of the time at which the signal started, but you can also use it to measure distance, as a measure of distance, right? Z is also a measure of distance. Yeah, co-moving distance, all co-moving indeed. Because if the signal had started, if you know when that signal started, right? You know Z. Suppose lambda, let's suppose the lambda of t is given. Somebody has given you lambda of t, right? In that case, what does it measure? That smaller t, right, would mean lambda of t would have been smaller, and hence Z would be larger, right? So by knowing Z, suppose you have received a signal with certain redshift, right? That tells us when the signal originated.
But that's if you know lambda.
Yes. Let's assume that you know lambda of t, right? If you know lambda of t, then knowing Z, you can figure out when the signal originated. Okay? But you can also figure out where the signal originated, right? Because if you know when, you also know where, right? Because light takes time to travel, right? And I'll try to make this explicit in the next few minutes.
This assumes that lambda of t is a monotonic function.
Yes, indeed. This assumes the lambda of t is a monotonic function. That we have not proven, but we will see it once we write down the answers. Indeed. I mean, let's take that for granted for now. The lambda of t is a monotonically increasing function.
But that's an input from GR.
That's an input from GR, indeed. So Z as a measure of distance. So you have already seen this equation, right? dr over square root of 1 minus kr square over a0 square is dt over lambda t. And imagine that we have the signal coming from minus, if the signal is coming from, if the R is reducing. So R naught to 0, dr over square root of 1 minus k r square over a naught square is integral u1 to t naught dt over lambda t. So if we know lambda t, this gives you R naught as function of T1. Right? It's implicit, but it will be some function of R naught. On this side, you have some function of T1, so you can solve for R naught in terms of T1. Right? So if we know lambda t, this gives you R naught as a function of T1. On the other hand, Z is given by 1 over lambda T1 minus 1. Signal left, yes. Okay, and I have put it T naught here because T naught is the same time when you are observing the signal. Yeah, this is what we are calling T1 prime earlier, right? But we take that to be today's time. Okay, so we also have Z equal to T1 1 over lambda T1 minus 1. So if you know the function lambda t, then T1 is known as a function of Z. So this gives you R naught as function of Z. Is that clear? Okay, so if you know the function lambda t, it will tell you that, and if you have calculated Z, if you have measured Z, it tells you where the signal originated, where R naught is, right? The distance of the source. And it also tells you the time at which the light started from the source. Now, in practice, it's actually reversed, right? We don't a priori know what lambda t is. But we can measure R naught as a function of Z as a function of R naught. Okay, we can identify distant sources, right? Measure that distance by some independent means, and then also measure the redshift directly. So what we measured is Z as a function of R naught, and using that we can figure out what lambda is as a function of t. Right? That's one way of determining lambda as a function of t. Yes. So R naught we have to find for some other astronomical physics, right? Like there are some something called standard candle supernova, type 1 supernova, right? Is what is called standard candle, and that means that their intrinsic luminosity is known, right? So if you find a type 1 supernova, right, and you can measure its luminosity, right, how bright it looks, right, and we already know what its intrinsic luminosity is, right? We know what the distance is because the luminosity goes down with distance, right?
Will those methods give us the co-moving distance and the proper distance to the object?
Well, proper distance, I don't know what you mean because proper distance is always 0, right? If you measure along the light travel path.
I mean, what I mean by proper distance at a given time.
Yeah, so that's what we are calculating, right? And that is what is the co-moving distance, right? This object. So you are asking, okay, I mean, it has traveled, the light has traveled, right? Yeah, so you have to do some work to reconstruct that, right? So, I mean, this formula that the luminosity also has 1 over R square, right? That assumes that the light travel time is almost 0, right? So that you have to correct for that, right? But nevertheless, if you know the luminosity, right? And if you know the intrinsic luminosity, you can figure out what the distance is, right? That's an independent measurement. Right? So that gives you a distance measurement, and then you calculate the redshift from that source, right? And that tells you Z as a function of R naught, and you can use that to find what lambda is as a function of T. Okay. So for example, these two H naught and Q naught, right, which requires knowing lambda as a function of T, are calculated that way, are measured that way, right, from observation on type 1 supernova. Are there questions?
Just to clarify this, so what are the measurements that we are doing to get some value to the power object are exactly the co-moving distance?
Well, you have to do some work to figure out, make sure that that's a co-moving distance. Whatever distance you measure, right, luminosity distance, how luminous it looks, right, apparent luminosity. Knowing that, you can figure out what the co-moving distance is. Right? You have to do some calculation because you have to see how much that power gets spread out over the whole sphere, right? And so what its apparent luminosity will be, right? So that way you can figure out what the distance redshift relation is. Sorry, so what is the distance luminosity relation is. Okay. Using that, you figure out what the co-moving distance is, and then use this formula. Right? So basically, the point is we need one function, right, to do this, and one function that you have directly from experimental observation is the apparent luminosity as a function of the redshift. Right? For every supernova, you can calculate its apparent luminosity, how bright it looks, and how redshifted the spectrum is. Right? Using that, so that gives a functional relationship between redshift and luminosity, and that you can convert into a relation on lambda as a function. Yes.
This apparent luminosity, you are saying, I mean, this relation might be complicated between co-moving distance of the object and this ratio.
Yes.
This might not be that trivial. Like simply
well, it's not trivial. You have to do some calculation, right? But as long as you know how to do proper light propagation in curved space time.
It's because when the light is traveling, this lambda is evolving.
Exactly. Exactly. It's because of that. Right? When the light is traveling, the lambda is evolving. Right? So it's not just 1 over r square, for example.
Yeah.
Right? That's so you have to correct for this expansion of the universe. Any other question? Okay. So the age of the universe I have already said. Age of the universe. So we choose the origin. Choose the origin of time. So that lambda is 0 at t equal to 0. Okay. And t naught is the value of t for which lambda of t is 1. Right? We had this reversing. We had said lambda of t naught is 1 by definition, but now we are saying that suppose you know the function lambda of t, right? Somebody has produced for you the function lambda of t, and you choose the origin of time so that lambda is 0 at time t equal to 0, right? And at whatever time t naught, lambda reaches 1 is what we call the age of the universe. Okay, and in the next lecture we'll write down the formula for the age of the universe. Okay, but this is the definition. Okay, the next important concept, and I think that then I'll stop for today, okay, is the notion of horizon, co-moving horizon. Oh, maybe one more thing I should have said. If you look at the metric, ds squared is minus dt squared. You see, for a co-moving object, right, these things don't change. R theta phi is fixed. Okay. So ds square is minus dt square. Okay. So for a co-moving object, t is the proper time, right? Because ds square is minus dt square, so t is the proper time of the co-moving object. So if you want to know what is the physical interpretation of the age of the universe, right, it's the co-moving time that has elapsed, right, from lambda equal to 0 to lambda equal to 1. Sorry, it's the proper time that has elapsed for a co-moving observer, right, who starts at lambda equal to 0 and waits till lambda equal to 1. Okay? That's the notion. That's the definition of the age of the universe. Right. So age of the universe always you measure in the proper time of the co-moving observer. Right, and that is natural because, as I discussed, most of the objects in the universe are almost co-moving. Right, their speed with respect to the cosmic microwave background is small compared to the speed of light. Is this clear? The co-moving horizon is the distance traveled by light since t equal to 0. This is a function of time. You start at t equal to 0, right? That's why lambda was 0. And then to calculate the co-moving horizon at any time, you calculate the distance that the light travels, okay, in a time t. Is the definition clear? Right? I'll write down a formula in a minute. So let's suppose the light starts at r equal to 0 and goes radially outwards. Okay, where you start, it doesn't really matter because the universe is supposed to be homogeneous, right? So origin point doesn't matter, but just for convenience, let's suppose that the light starts at r equal to 0. Then you have this equation dr over square root of 1 minus a square over a0 square r square is dt over lambda t dr. Thank you. And this time I have not put a minus sign because the light is going outwards. As time increases, r increases. Right? So I have not put the minus sign. So RH, so the formula for RH is the integral 0 to RH dr over square root of 1 minus a square over a0. Pardon?
It's K, not K.
Not
K square.
okay. Oh, thank you. Yeah. Okay. K over a0 square r square is integral 0 to t dt prime over lambda t prime. So this gives you RH as a function of t. Or let me call this, sorry, let me call this R naught, right? This is the distance. This is my definition of RH. Okay, let's imagine that it goes from 0 to some R naught. Right? We don't know what R naught is, but this quantity is the distance around the spatial slice. So this is the formula for RH. RH at t Okay, so if you know lambda of t, right, you know how much distance it travels in time t. How much distance the light travels in time t. Is this clear? Okay. Now here there is a qualification that is needed. Okay, which is, I said how much distance it travels, but let's see what it's really doing. ds squared is minus et squared plus lambda of t squared dr squared over 1 minus k r squared over a0 squared plus so we have defined RH as integral 0 to r naught dr over square root of 1 minus kr square over nr square, right? So this is the distance measured in today's metric. Because today lambda t is 1. Right? So if you are using the metric today, right, the point r naught would have been this far away. Right? That's why this is RH is called co-moving horizon. Is this clear? Now suppose you want to calculate the metric, the distance measured by the metric at time t. Right? That's what RH means. That's why you're calculating the horizon, right? How far light has traveled. In that metric, the distance at time, the distance measured in the metric at time t, how much will it be? Right? That is the physical horizon. Let me call this by dH of t. Any suggestion how much it should be? It will reach the same point R0, right? At time t. That is not going to change. It's only a question of the how much that distance between 0 and R0, right, means by the metric at that time. Yes. So here I calculated this quantity, right, which I defined as RH. This is an equation that you can write down, right? And this RH by definition is this one. Okay, I integrate from 0 to R naught. I assume that it reaches R naught at time t, and I integrate it from 0 to t. Okay. So this gives you RH as a function of t. Okay. The question is, what is the physical meaning of RH? Right? I calculated this integral, right? But what is the physical meaning of this integral? Right? The physical meaning of this integral is the distance, and you can say from the metric form of the metric that is a radial distance, that the distance that the light has traveled. Okay? But there is a factor of lambda t square, right? So this is the physical distance if we measure it using today's metric, because today lambda of t is 1. Is that clear? R naught is how far in the R coordinate, how far the light travels. If we set k over a0 square equal to 0, then R naught is the same as RH. Right? I have kept R naught because I have not set k equal to 0. Right? But for all practical purpose, R naught is the same as RH. Okay. So let me physically say again, the universe starts expanding at t equal to 0, right? Imagine that at t equal to 0, there is a point at the origin and some light starts. right? We wait for time t, right? And in that time, the light ray travels, right? We are asking up to what point it travels in the coordinate space. That's R naught. Now, what distance does it correspond to? Right? And this quantity that I have written is the distance to that point from the origin, right? But measured in the metric with lambda equal to 1. Right? But at time t, the metric was not with lambda equal to 1, right? Lambda t was smaller at time t. Right? So suppose I want to calculate the physical horizon size, right? What an observer at that time would have seen as the horizon size. You should take where will you put the lambda? Inside the integral? Yeah, see, inside the integral will be hard, right? Because then we might as well put it on the other side. Lambda square. Yeah, is that the correct answer? See, you think physically, light has started at the origin, r equal to 0, right? Light starts traveling outwards, right? There's nothing wrong with this equation, right? Because this equation is telling us how much the coordinate is changing as the light is traveling outwards, right? So there is no doubt that light at time t reaches the point r naught that is given here, right? So determinants of r naught has no problem, right? If you know r naught want to know r naught as a function of time, it's this equation. Okay. The confusion is because you have to convert this to the actual physical distance that it corresponds to. 0 to r naught, right? How much physical distance does it correspond at time t? Multiply that by the scale factor. So the physical horizon is lambda of t times RH. Is this clear?
So
Yes. It's the simplest possible answer you can think of, right?
I think I asked this in last course as well.
Yes.
So the way RH is defined, it is if I take a meter scale
Today.
today, long enough,
Yes.
and measure the distance, that will be
The RH.
that will be RH.
Yes. Today, imagine that light had traveled up to certain distance, right?
Yeah.
At some time in the past, right? That point you fix it. It's a co-moving point. So you mark that point in the co-moving coordinate, right? You wait till today and take a meter scale to measure the distance up to that point. That is RH.
If I measure, it will be
RH.
It will be RH. But what is then DH?
DH is that when the light, suppose somebody took a meter scale at that time,
Okay.
right? And measured this distance.
Okay.
So the meter scale has to be done using atoms and molecules, right? Not by physical meter, because there's nobody there to use physical meter. But take the wavelength of some light at that, right? And measure this distance. That will be this lambda of t times RH.
Telling me it's bigger.
No, it's smaller. It would have been smaller.
Okay.
It's smaller, right?
DH is smaller than RH.
DH is smaller than RH. Right? Because you are talking about t less than today's time, right? If we consider t larger than today's time, then DH will be larger than RH. Right? So it seems from this perspective that DH is the physical object, right? Why should you care about RH? But RH is a very useful tool, right? So you should keep this in mind and we will use it when I need it, right? Because we want to convert everything that happened in cosmology, right, into today's scales. Because what we can do, you can do the measurement only today, right? We cannot go back in the past and do measurement, right? All the measurements are being done today. So it's useful to convert everything in today's scale, right? So that you know in the today's co-moving frame where exactly that point was, right? Where light would have reached sometime in the past. Right? That's the information that RH contains. Okay, so I think today I'll stop, and tomorrow then I'll start reviewing the equations that determine lambda. right? Because so far I have only talked about that somebody gives you lambda and then what you can do with it, right? So tomorrow you have to know how to determine lambda in the first place, right? And for that you have to examine the Einstein's equations. Okay, so right now I'm not changing any of the class timings till this graduate committee fixes some slots, and then we'll just move into that slot.